All right, it's time for us to put our money where our mouth is, and we're going to talk about determining an empirical formula. So let's just remember empirical formula is the smallest whole number ratio of a formula, right? The smallest, whatever. As long as it's a whole number ratio, it's the smallest one possible as we figure that out, okay? So let's take a stab and see what we got to do this, okay? We're just going to work a bunch of things. Here we go. We're going to have, there's lots of ways in this to do it. Here we're going to start us off with a gram example. So the goal here is we have to remember that the formula of a compound doesn't relate to grams, it relates to moles. So our big idea is we've got to get grams to be moles, and then somehow we can take our moles and get a formula, okay? So when we're doing this, this is the plan we're going to go, okay? Let's see. So we're given this many grams of hydrogen and this many grams of oxygen. So let's get it there. I already screwed it up. Okay, 0.857 grams. And then we have to get this to moles. So 1 mole of hydrogen is 1.008 grams. Okay, we'll do the same thing for oxygen, 6.86 grams. And that, oops, sorry, one mole of oxygen is 15.998 grams. Okay, turn those guys into moles. We'll figure this out. All right, so 0.857 divided by 1.008 is 0.850198. I'm leaving some digits on here because I'm not thinking about it right now. This is hydrogen. Okay, 6.86. I didn't put it on everything in there because they're all the same as we do it. 998. It's just we don't want to forget what units or what what number is what element. 428,803 moles. This is oxygen. That's an 8. All right. Now we've got our moles. So how we turn the moles into the formula is really we just need to know the ratio of the two to each other. So what we're going to do, and they're going to do this every time we do an empirical formula step somewhere, is we're going to divide by the smallest, and that's going to give us our ratio. Okay, so here the smallest is oxygen. So we're going to take this, and if we divide this by itself, that means we're going to get 1.00 oxygen. Our ratio has to have the right number of significant figures because this has 3, this needs to have 3. Okay, to do hydrogen, we're going to divide this by the oxygen one, 428,803 moles of oxygen. I'm going back into my calculator and dividing the actual two numbers, so I'm getting a lot more digits in my calculation than I'm showing here. But that should work. Okay, so this gives us, and again, we want 3 significant figures for this. So this is 1.98 for hydrogen. So ultimately what this is telling us is this compound is hydrogen 1.98, oxygen 1.00. You can think of it that way, but we need whole numbers. These are not whole numbers. So we can actually round some of these, right? This is 0.98. That's close enough to a whole number here. So we can call this H2O. We figured out water. There we go. Does that make sense? We're going to use this process for most of our things. Okay. That's if we're given grams. You could also be given percent, right? This is percent composition, what we talked about in another video. We talked about percent composition. Percent composition is the data you get by doing an experiment usually, or sometimes you can send out a compound for analysis, and the analysis will tell you what the percent of each element is. Okay, so in this example, we've got a compound that contains sulfur and chlorine, and we know the percent sulfur is 31.14%. All right, so we need to figure out percent chlorine. So our percent chlorine, remember our total percentage is always 100. So our percent chlorine is going to be 100 minus 31.14%. I'm not going to put the percent in there, to give us how much chlorine is there. So 100 minus 31.14 gives us 68.86%. And that's chlorine. Okay, that's step one. Sometimes you'll be given all the percentages. Sometimes you have to figure one out, but the total is always 100. Okay, now that we have both percentages, we need to get to, somehow we have to get percentages to moles. Okay, remember, because moles are going to lead us to a formula. For getting percentages to moles, we have to have something in between. Remember, this is a mass percent. So what this means is we can take our percent, turn it into grams, take our grams, turn it into moles, take our moles and turn it into a formula. Okay, grams to moles to formula is what we just did in the water example we had a minute ago. Percent to grams is a new step. Okay, now you can assume whatever total mass of sample you want. So you want to assume 85 grams is your total sample, do it, that's fine. You would have to convert. What is 68.86 of 85 grams? The easiest way to do this is we're going to assume that we have 100 grams total. And when we do that, when we assume we have 100 grams total, then the percentages are equal to the grams. And so we can skip, quote unquote, skip this step of getting percentages to grams and just write our percentage down as grams. So for sulfur, we have 31.14 grams. Okay, in grams to moles. So 1 mole of sulfur is 32.605 grams. For chlorine, now that we have grams, this is the same as what we just did a minute ago. 68.86 grams, and 1 mole. My multiply sign looks dumb. Chlorine 35.450 grams. Okay, so we'll math it out. 31.14 divided by 32.605 is 0.955068 moles. This one is sulfur. And then 68.86 divided by 35.450 is 1.94254 moles of chlorine. I'm not rounding right now. We're going to round in a bit here. Now that we have our moles, to get our moles to be formula, we have to find the ratio of the moles. So again, we're going to divide by the smallest. Here, the smallest is the sulfur. So we're going to divide by that guy. Okay. Dividing sulfur by sulfur means this is going to be 1.000, 4 significant figures, because our percentages had 4 significant figures, sulfur. For chlorine, we'll take the chlorine moles and divide it by 0.955068 moles of, well, it doesn't matter. The moles matter, but the sulfur doesn't matter. All right. So we take our chlorine moles, which is that number, divide it by our sulfur moles, which is that number, and we get to 4 significant figures, 2.034. Okay, so what this says is for every 1 sulfur, there are 2.034 chlorines. That's close enough to 2, we can round it. So this should be SCl2, because there's 1 sulfur and 2 chlorines. Okay. All right, there's one more thing I want to work with us while we're here talking about empirical formulas, and that is something called a metal oxide problem. You're going to do this in the lab if you're with me. You're going to do this in the lab, not with this exact setup, but you're going to figure out a metal oxide empirical formula. Okay, this is a pretty general procedure, and you can see variations of this throughout homework and whatever. But essentially, as long as you have a 2-component system and you're doing a system like this, the problem will work the same way. And it's very similar to what we've talked about already. Okay, just a little bit of reading the problem and interpreting what it says to get us through it. Okay, so if we look at this, we have some grams of yttrium is reacted with pure oxygen, and that's completely converted to its oxide compound. So somehow we have yttrium oxide. So we can make a note here and say that this is yttrium with some, I don't like X. Let's use yttrium with some subscript and oxygen with some other subscript. And we got to figure out what those subscripts are. Okay. At the end of the experiment, we have this many grams of oxide product produced. So these are the numbers we have to work with. This much of yttrium at the start and this much of oxide compound produced at the end. Okay. So this is the total mass. This is how much yttrium is there. We're not losing any yttrium. Remember, law of conservation of mass. Everything we put in there has got to be there at the end. So we can figure out oxygen by subtracting, okay? Because oxide is not the oxygen in the compound. That's the total mass of the compound. So first off, we're going to find grams of O, okay? And we're going to do that by subtracting. And we do that by saying 1.1767 grams of oxide minus 0.9266 grams of yttrium. Okay, so this means 1.1767 minus 0.9266 is 0.2501. 0.2501 grams. This is grams of O. Now, it's the same problem we just did. Grams to moles, moles to formula. We have to get a ratio to get to the formula, okay? The grams we want to be able to do that are the grams of yttrium and the grams of oxygen. And we're going to turn both of those into moles. All right, so 0.9266 grams yttrium. Let's see, 1 mole is 88,906 grams. Then we do oxygen, 0.2501 grams. And 1 mole of oxygen is 15.998 grams. All right, math machine now, 0.9266 divided by 88.906 is 0.104222 moles. This is yttrium. 0.2501 divided by 15.998 is 0.1, oops, nope, 0.01563332 moles of oxygen. All right, now we're almost there. We need to get our ratio. Remember, to get the ratio, we're going to divide by the smallest. In that case, our smallest here is the yttrium. No. Oh, no, that's right. There's supposed to be a 0 in front of this because apparently my brain is ignoring these zeros. So this should be 0.010. Okay, so the yttrium is the smaller one. Yes, okay, good. Now that I've fixed my screw up, yttrium is our smallest. So that means the yttrium is going to be 1.4 significant figures. So this is going to be 1.000 yttrium. Okay, I'm putting it down here just because I ran out of room. All right, then we have our oxygen. Oxygen divided by the yttrium, 0.0104222 moles is, let's see, oops. Oxygen divided by this one is 1.49998. Okay, this is oxygen. All right, so can our formula be YO 1.5? No, because we have to have a whole number multiple. Okay, so what are we going to do instead? Well, we have to keep the ratio of 1 to 1.5 in our answer. Okay, since we can't have 1.5, if we multiply it by 2, what we'll get is Y2O3. That's still a ratio of 1 to 1.5, and it's the lowest whole number multiple. So this is our answer, Y2O3. Okay. I hope that made sense. You'll see metal oxide problems a lot from me. It doesn't have to be oxygen. It doesn't have to be yttrium. It can be whatever. Something, it doesn't have to be a metal. It could be a non-metal, right? Something is reacted with something else, makes a binary compound, and you know the total, and you know one of the things. This is the process on how to do it. All right. If you have any questions, let me know, and I will catch you later.